Hello friends. Picture this. You're holding a hand of playing cards and they're all out of order. What do you naturally do? You pick one card, look at the cards to its left, and slide it into the right spot. Then you grab the next one and do the same thing, one card at a time, until the whole hand is sorted. That instinct you already have. That is insertion sort. In this video, we are going to unpack exactly how that idea becomes a real sorting algorithm, trace it step by step through an example, and look at when it shines and when it slows down. No experience required. Just bring that card sorting brain. Next, let's build the mental model that makes this click. Alright, so here is the core idea behind insertion sort, and it is simpler than you might think. Imagine your array is split into two regions at any given moment. Everything to the left is already sorted. Everything to the right is unsorted and waiting its turn. Now you pick the first element from the unsorted region. That is your current element. You carry it in your hand, and you walk it leftward through the sorted region, comparing as you go. Any element larger than yours slides one step to the right to make room. The moment you find an element that is smaller, or you reach the very start, you drop your element into that gap. That is it. One pick, a series of shifts, one placement. Next, we will trace this exact process through a real array, step by step. Alright, let's trace through a real example. Our array is 5, 2, 4, 1, 3. Pass 1, we pick 2. It's smaller than 5, so we shift 5 one spot to the right and drop 2 into position. Sorted region is now 2, 5. Pass 2, we pick 4. It's smaller than 5, so 5 shifts right. But 4 is larger than 2, so we stop. 4 drops in. Sorted region is 2, 4, 5. Pass 3, we pick 1. It's smaller than everything. 5 shifts, 4 shifts, 2 shifts. 1 drops all the way to the front. Pass 4, we pick 3. It slides past 5, past 4, then stops behind the 2. Done. Final array. 1, 2, 3, 4, 5. Every pick, every shift, one comparison at a time. Next, we'll turn this exact trace into real code. Alright, now let's see those same ideas in actual code. Here's a clean insertion sort written in C++. The outer for loop starts at index 1 and walks to the end. That is our pick the next unsorted card step from earlier. Inside, we save the current element into a variable called key. That is us holding the card aside. Then the inner while loop looks left and shifts any element that is greater than key, one position to the right, exactly the make room motion we traced by hand. When the loop stops, we drop key into the gap. Every line maps directly to a move you already watched happen on that small array. The structure is simple, because the mental model is simple. Now that the code makes sense, let's find out what it actually costs to run. Alright, now that we have seen the code, let us talk about how fast it actually runs. Start with the best case. If the array is already sorted, each element only needs one comparison before it settles in. That means the work grows directly with the size of the array. Big O of n. Linear. Fast. Now the worst case. A reverse sorted array. Every new element has to travel all the way back through every sorted element before it. That compounds quickly. Big O of n squared. Slow on large inputs. Average case lands at big O of n squared too, because on random data you still end up doing roughly half those comparisons per element. Here is the good news though. Space complexity is big O of 1. Insertion sort sorts in place, using no extra array at all. Next we will look at exactly when that trade-off works in your favor. Alright, let's bring it all together. Insertion sort is simple, stable, and works in place, meaning it needs no extra memory. It runs in linear time when the data is already nearly sorted, which is genuinely useful in practice. Where does it shine? Small lists, nearly sorted arrays, and situations where new elements arrive one at a time, like a live leaderboard or a hand of playing cards. It handles those cases elegantly. Where does it struggle? Large, unsorted data. That order n-squared average and worst case becomes painful fast. For anything sizable, you would reach for merge sort or quick sort instead. The key takeaway: know your data. Insertion sort is not a toy algorithm. It is a sharp tool for the right job. Thanks for watching, friends. See you in the next one.